a few minutes late. Well, I got them back to back to back today, so it's hard to get from one out of one and into another.
Oh, no worries. No worries. Yeah.
I'll try to remember, and we'll go like 5 minutes later because I don't have anything at 7:30. Um, so have you gotten to the unit circle yet?
No. Today we got to converting radians to degrees and degrees to radians.
Right. For some reason, math in all levels, from algebra to geometry to precalc to trig to calculus, always tends to start you out with tougher material and then get easier. I'm not sure what the purpose of that is. I hate it myself, the fact that they do that. If I was teaching trig, I would start with the unit circle just like I started with you on Monday.
Yeah.
So you'll get to the unit circle. It may not be till...
We're doing it Friday.
Okay. All right. You'll be miles ahead with what we did on our first session. So
yeah, I think I will.
Let's talk about what to do today. Do you have some specific problems?
Yeah, I do. I'm just I have an online textbook now that they gave us. So
Okay.
I'm just still figuring it out.
I'll give you just a few tips, first of all.
Okay.
Knowing what these are is extremely valuable. These four. That is 90 degrees, that is 60 degrees, that is 30 degrees, and that is 45 degrees. Notice that this number by times this denominator is 180. All four cases. Okay? So all I'm going to give you is a little bit of an easier way to convert radians to degrees. So if pi over 3 is 60, what is 2 pi over 3?
Pi over 3 is 60. 2 pi over 3.
Twice.
Pi over 3 would be, yeah,
2
120.
pi over 3 is twice as much as pi over 3. Got to be 120. In other words, if the numerator is not just pi, then these two numbers do not multiply to 180.
Okay.
They multiply to 180 when you have just a pi in the numerator.
Okay.
What's 4 pi over 3?
4 pi over 3 would be 240.
Yeah. Now, to me, that's a much easier way of doing it than the way they teach. I still am a very big believer in the way they teach. In other words, if I'm doing this the normal way, I've got radians on the left. Oh boy. And then this eraser stopped working. I never have understood why. If I'm going to convert this, I know I'm in radians because it's got a pi, right?
Yeah.
Oh, man, hold on. So the conversion factor is pi over 180 or 180 over pi. And what it really is pi radians over 180 degrees, and this is 180 degrees over pi radians. So the official way to translate from one to the other is to use one of these conversion factors. And the one you pick is the one that gets rid of what you want to get rid of. In other words, in our case here, I want to convert all of these to degrees. So I want to lose the radian, right? Well, the radian's in the top right now, which means it's got to be in the bottom. I got to use that conversion factor.
Yeah.
Because the radians go away, and I'm left with degrees. And the pi's cancel, so I'm left with 90 degrees. Okay? And I can do these harder ones like 2 pi over 3. That's in radians. So I need the conversion to have radians in the denominator. And I can still do it relatively easy. The 3 cancels and makes that 60, and I end up with 120. So I can still get to my same answer. And certainly for your tests, they may want you to do them all precisely this way, using either pi over 180 or 180 over pi. Okay?
Yeah.
Notice that if I'm going the other way, let's say I have 45 degrees and I want to convert that to radians, well, what's my conversion factor?
Pi over 180.
And 45 goes into 180 4 times, so I end up
So it's 1/4.
Radians. Now, radians are a peculiar thing. They probably made that really confusing for everybody also. Remember last time I said that radians and degrees are not like feet and meters or gallons and liters. They're fundamentally different. There is a conversion factor between radians and degrees, but they are fundamentally different. And it's not necessary for me to really explain what that difference is, because that's probably an hour lecture right there. But fundamentally, the difference is radians are numbers.
Okay.
Degrees are slices of a 360-degree circle. So radians are far more valuable. And when you get to calculus, calculus only works on radians. You can't use degrees. You can't take the first derivative of the sine of 45 degrees. You've got to convert it to radians to figure out what the first derivative is. So once you get to calculus, everything's going to be in radians. And they may give you a problem in degrees, but you might have to convert it to radians to proceed.
Okay.
Up until then, you'll be dealing in both. In other words, for the first half of trig, you'll deal in degrees and sometimes in radians and others. And radians will almost always have a pi. Not always. You can have 3 radians. That's an angle. Okay? So it doesn't have to have pi in it, but it generally does.
Okay.
All right. Specifically, what problems do you have that we can work on?
So this first one is identify all angles that are coterminal with the given angle.
Okay.
Then find and draw one positive and one negative angle that are coterminal with the given angle.
Okay.
So the first given angle is negative 75 degrees.
Okay. Let's first of all graph that. Remember, it's a negative, so I'm going to go clockwise. That's 75 degrees right there. Now, to get the coterminal angles, if I want, there's an infinite number of coterminal angles. I could add 360 and add another 360 and add another 360. They're each coterminal. But since they want a negative one and a positive one, well, if I add 360, that'll give me the positive one. And if I subtract, that'll give me a positive one. And if I subtract 360, that'll give me the negative one. Well, what's that one?
The added one? 285.
Okay, so that's coterminal with minus 75. There's a difference of 360. And the other one?
Negative 435.
That's also 360 different from that.
Okay.
Right? If I subtract 360 from this, I get minus 75. So there's one positive and one negative. And you actually had multiple answers. That's not the only answer. I could add another 360 to that, and I get 645. Well, that's one answer also. 645 is coterminal with minus 75. But usually when they ask for a positive and a negative, they want the smallest positive one and the smallest negative one. And that is the smallest negative one that's coterminal with minus 75.
Okay.
Now, graphing them. The 285, here, let me erase this just so I don't confuse. The 285 turns out to be that angle right there always.
Mm-hmm.
And the 435, I basically go around twice. That is minus. Notice that I started going clockwise from the x-axis, and I went around once entirely. That was minus 360. And then I went around another 75 to get minus, that's minus 435. Notice that both coterminal angles end up on the same ray. In other words, the positive one ended up there, and so did the negative one. And that will always be the case.
Okay.
Your trig functions of coterminal angles are always the same as the trig function of the coterminal angle. The sine of minus 75 is going to be the same as the sine of 285.
Okay.
Okay? All right, what else they got?
Okay, the next one is negative 3 pi over 4 is the degree, and they want the same thing.
Okay. Now, most people who go through trig go through a period where they convert everything to degrees, work in degrees, and either convert it back to radians when they're done or leave it in degrees. When they give it to you in radians, they want their answer back in radians. Well, in this case, 360 is the same as 2 pi. So my positive one is going to be added to pi, and my negative one is going to be subtracting 2 pi.
Okay.
It's the same as 360 degrees. Each pi is 180 degrees. Okay? So if I'm labeling my axis here, I'm not going to label that 90. I'm going to label it pi over 2. I'm going to label that pi instead of 180, and I'm going to label this 3 pi over 2 instead of 270.
Okay.
Okay. Well, minus 3 pi over 4, remember each quadrant is pi over 2. So if I'm starting from the x-axis and I'm going clockwise, I got to go to pi over 2 to get to that, and then I got to go another pi over 4 to get to that. This is a case where you'd see it a little bit better if I converted it to degrees. 3 pi over 4, because I know pi over 4 is 45, 3 pi over 4 must be 135. To me, that little trick in converting really saves a lot of time. If you always remember what pi over 2, pi over 3, pi over 4, and pi over 6 are. It's all you have to memorize, and then you can convert them to degrees quite easily. So this angle is minus, because it's clockwise from the x-axis. When I add 2 pi, what do I get? To minus 3/4 pi.
You get negative 12/4 pi.
The top one only. In other words,
we're adding?
Common denominator, so that's going to be 8 pi over 4.
So you get 5 pi over 4?
Yeah.
Sorry, I did the bottom one.
It's okay. And that angle is always that one, the counterclockwise angle.
Yeah. Okay.
ending up at the same spot.
Okay.
Now if I do the other one, I got minus 8 pi over 4, so I got minus 11 pi over 4.
Oh, 11.
Minus 3 minus 8 is minus 11. And
Mm-hmm.
what this one's going to be is, since it's a minus, I got to go clockwise. And I go a full 2 pi plus another 3 pi over 4 to get there.
Okay.
So that red is minus 11 pi over 4. And I converted the first one to degrees just because I still think better in degrees than radians also, despite the fact
Mm-hmm.
I've been tutoring trig for 8 years. Although I'm close. I'm close to be able to think in radians only. And you'll get to that point where you'll be able to think in radians only. And
Okay.
you'll recognize that 3 pi over 4 is 1.5 quadrants.
Yeah.
Okay? So again, there's my positive one, there's my negative one. The smallest of each.
Okay.
Okay, what else we got?
The next one's talking about intercept arc
Okay.
length.
Mm-hmm.
So it says find the length of the intercepted arc with the given central angle measure in a circle with the given radius.
Okay.
Round to the nearest tenth.
Okay.
And it is pi over 6 with a radius of 2.5 meters.
Polar coordinates, that's the way I'd write it. That's the radius, that's theta.
Okay.
Okay, now I know you haven't got to polar coordinates yet, but it's a similar coordinate system to the XY coordinate system, only all the radiuses are positive. And that's why the unit circle, it's always +1 no matter which quadrant you're in. Okay,
Okay.
now there's a general formula for arc length. S equals r theta if theta is in radians. If theta is in degrees, I got to convert it to radians. And the way I would convert it, if it was in degrees, would be to multiply it by pi over 180, right?
Mm-hmm.
If it was in degrees. So here's your two key formulas. For determining arc length. Well, the problem they gave you, it's in radians, so we can use the easy one, the top one.
Mm-hmm.
So arc length is the radius times pi over 6. Now, if I want to simplify that a little bit, I can multiply top and bottom by 2, which gives me 5 pi over 12, which is a little nicer looking. In general, you want to use whole numbers, not decimals when you're talking.
Yeah.
So this 2.5, I can change it to 5 halves, and that also gives me 5 pi over 12. And what that means is the following. I have a circle that has a radius of 2.5. Pi over 6 is what angle?
Pi over 6.
The easy way, not the hard way.
Pi over 6 is what? 92, 63. Oh, man.
It's got to be 30. In other words,
Okay.
whatever the degrees is, times 6 has to equal 180. It's just,
Okay.
remember pi over 2 is 90. 90 times 2 is 180. Pi over 3 was 60, because 60 times 3 is 180. So when I say the easy way, that's the easy way to do it. It's 30
Okay.
degrees, okay? Well, if I draw a 30-degree angle, and I'll even label it pi over 6, what they're measuring is that. That is S. And by that, I mean if this circle was made out of a piece of string and you cut it at these 2 points and straightened out the string, that's what they're talking about. That's arc length. It's not
Okay.
the straight line distance between those 2 intersection points. It's the straightened out distance.
Okay.
Okay? And just so you know, let's figure out a really easy one. 2-inch radius. What would the arc length of the entire circumference be?
Isn't it just 2 pi?
Times 2 pi.
Oh, times.
2 pi r, right?
Okay, yeah.
So that would be 4 pi. That's the arc length.
Okay.
It's the arc length of the entire circumference. And does that follow our rules? Well, what's the angle we're dealing with? The angle is actually 2 pi, is it not? It's 360 degrees. Well, S equals R times theta. R is 2, theta is 2 pi, so I get my 4 pi whether I'm using the equations from geometry or from trig.
Okay.
And this is a good little method to verify that you're doing it properly. In other words,
Okay.
you always know what the circumference is because you've had geometry. Well, the entire circumference is the arc length of a 360-degree central angle.
Okay.
So if I had a 270-degree central angle and I want the distance from here to there, I could just find the circumference of the circle and multiply it by 3/4, right?
Yeah.
Or I can use this equation here. And they'd like you to use these equations here.
Okay.
Just remember, the simpler one, it's in radians. And the more complicated one is in degrees using the degree to radian conversion factor.
Mm-hmm.
So
Okay.
really the only one you have to memorize is that one. Just make sure that you're in radians if you're using that one. If you're in degrees, you can still use that one and then multiply it by pi over 180, the conversion factor.
Okay.
Okay? All right, what else you got?
All right. The next one is a carousel at an amusement park rotates 3,024 degrees per ride.
3,024 degrees per what?
Ride.
Okay.
It wants to know how far would a rider seated 13 feet from the center of the ride, from the center of the carousel travel during the ride.
Okay. So we can take that as the central angle.
Okay.
And remember, what's our formula? S equals what?
S equals R theta.
R theta times pi over 180, because we're
times pi over 180.
We're in degrees. And S is the arc length. Well, that rider that's seated 13 feet from the center is going to go around and around and around about 8 times, right?
Mm-hmm.
I can figure it out by just plugging it into this. R is 13, theta is 3,024, and the rest is calculator stuff.
3,000.
I'll bet you that ends up being a whole number. 13 times 3024 divided by 180. Don't put your pi, when you're doing this on a calculator, leave pi out and add it at the end. You never,
Yeah.
you never really want to convert pi to a decimal. You're approximating it if you do. And if you want the exact distance that the rider rides, then you want to leave it as pi. So what'd you get when you multiplied this times that and divided by 180?
Oh, whoops. I multiplied the first one wrong.
Not by pi. Leave the pi out. We're going to add the pi, but we don't want it in there because it's just going to confuse your calculator.
Yeah, I got 218.4.
Really? 218.4
Yeah.
times pi, right?
Yes.
Okay, that's the distance the traveler is going to go. Now, let's see if that makes sense. What do you get when you divide that angle by 360?
Divided by 360, 0.6,
No?
like 0.6066,
No.
line above the 6.
3,024 by 360.
Oh, okay. 3024 divided by 360 equals 8.4.
That's the number of revolutions that rider's making.
Okay.
Right?
Yeah.
He's going to go around. One ride is 8.4 revolutions. Well, each revolution is the circumference of a circle that's 13-foot radius. So he's going 2 pi times the radius, 13, each revolution. So he's going 26 pi. So if I multiply 8.4 revolutions by 26 pi, the distance he covers with each revolution, I get this same answer over here.
Okay.
If you multiply that by that, you'll get 218.4.
Okay.
Now, the only mistake you can make with these problems is either leaving the pi out because you forgot to put it back in, or putting it in the first place because it's going to round it off. When you use the pi key on your calculator, it doesn't actually use pi. It rounds it off to like 9 decimal places and gives you an answer. So if you were to actually put pi in there, you might end up with a number that has a little round off error in it. So that's why you leave it in terms of pi. And that's the proper way mathematically also. If you have a teacher that's saying, give me a number, not, round it off to 2 decimal places, well, then you have to put pi in there, and whatever number that comes up with, be about 600 and something, and then round it off. But most teachers will not only want you to leave it in pi, but will seldom ask you to convert it to a decimal.
Okay.
Okay?
Okay. The next one is, it's like conversions of radians, hours, and other such.
Okay.
So it is, find the rotation in revolutions per minute given the angular speed and the radius given the linear speed and the rate of the rotation.
Okay.
Go
ahead.
35 is W equals 135 pi.
I was writing.
Oh, sorry, that was the number of the problem.
W equals what?
135 pi, and then radians divided by hours.
Radians per hour?
Yeah.
Okay. And W being?
It doesn't give us what W is.
Rotation rate. That's the angular speed. W is angular speed.
Okay.
In other words, if I have a wheel that I can turn twice an hour, its angular speed is 2 revolutions per hour.
Okay.
Okay. Now, what you have to do here is apply a number of conversion factors. What was the original question? All of it again, read.
Find the rotation in revolutions per minute given the angular speed and the radius given the linear speed and the rate of the rotation.
Okay. So we need to take this angular speed and convert it to revolutions per minute instead of radians per hour.
Okay.
Okay. And the way you do all conversion problems is by making sure that you end up with, what was it again, revolutions per minute?
Yes.
Okay. So we want to take this angular speed and convert it to revolutions per minute. Well, the first thing I'm going to need is to get rid of the hours. How do I get rid of the hours? Between hours and minutes.
There's 60 minutes in an hour.
Okay, but notice that if I write 60 minutes per hour, that does not get rid of the hours. I need the hours in the numerator.
There are
1 hour per 60 minutes.
1 hour per 60 minutes, okay.
In other words, all of these conversions, you can flip them and they're just as valid. If it's 1 hour per 60 minutes, it's also 60 minutes per hour, and so forth and so on. The secret is to know to write it 1 over 60 or 60 over 1, because it's going to make a big difference to our answer. I wrote it 1 over 60 because I know I want to lose the hours.
Okay.
Now I got radians per minute. Well, I'm getting closer. What's the ratio? What's the relationship between radians and revolutions?
Radians and revolutions. Isn't it like 2 pi radians equals 1 revolution?
How do I want to write it? I want to write it like that.
2 pi over radians?
Yeah. No. 1 revolution is 2 pi radians.
Oh, okay.
I write it like that because I know the radians are going to cancel. Now look what my units are. They're exactly what I need them to be. I'm left with nothing but revolutions in the top, and I'm left with nothing but minutes in the bottom. Now I just got to multiply all the numbers together. Notice that pi cancels with that pi, and I end up with 135 in the numerator, and I end up with 120 in the denominator. So whatever that number reduces to, I guess I can divide it by 5. So it reduces to 27 over 24. I can reduce that further. I can divide it by 3, so it's 9/8 revolutions per minute.
Okay. Oh.
Some of these
I think I see how you did that.
Get really hairy. I've got one in my book that there are 5 conversions needed. In other words, they give you the angular speed of a wheel and the radius of a wheel, and they want you to figure out what its linear speed is.
Oh.
In other words, that's the way you do it. If you have a wagon that's got wheels like that, and I know the radius of that wheel is, say, 2 feet, and I know that that wheel is turning at 3 revolutions per minute, I can tell what the linear speed of that wagon is by applying a number of conversions. And the radius of the wheel is a part of it.
Okay.
Okay, in other words, we got revolutions per minute, which is still an angular speed. That's not a linear speed.
Mm-hmm.
That's angular speed. It's rotating at 9 revolutions per 8 minutes. It's making a complete turn 9 times in 8 minutes. And linear speed, I would have to apply all of there's 5 conversions involved, and I could come up with what the linear speed of that wagon is. You can do the same thing with a car. If you know the radius of the wheels of your car, and you know how fast they're turning, then you can figure out what the linear speed of the car is.
Okay.
Okay. Now, I seem to remember you mentioning linear speed when you read this problem.
Yeah, it's the next problem.
I was going to say, to just come up with revolutions per minute, that's not linear speed.
No.
Okay, hold on 1 second. Rather than me working them all out, it's going to be easier if I just go to the page that has angular speed and linear speed. All right, what's the problem? The next one.
Okay, so the next one is, I think this is the one where it wants us to convert it to like linear speed.
Yeah.
Or it wants the radius given the linear speed and the rate of rotation. So,
Okay, that's really hard. Okay, go ahead. Here, I tell you what.
sorry.
I'm going to go through my example, which is your problem half as hard, just to show you what I mean. And then we'll tackle your problem. Okay, here's my problem. This guy's got a truck that have 36 inches, wheels that are 36 inches in diameter.
Mm-hmm.
And the wheels are rotating at 630 revolutions per minute. Find the truck's speed in miles per hour. Okay, so we start with 630 revolutions per 1 minute.
Okay.
Times, and we want the final speed to be in miles per hour. That is a linear speed, right?
Yeah.
You can tell by the units whether it's angular or linear. Angular is always going to be some number of revolutions or radians. Linear is going to be miles per hour or feet per second or something like that.
Mm-hmm.
This particular problem wants his speed in miles per hour. So the first thing I got to do is get rid of the minutes. What's that conversion factor? To get to hours?
To get to hours, you would want minutes in the new. So 60 minutes per hour?
Yep. Not 1 hour per 60 minutes, because I want to make sure the minutes cancel.
Yeah.
Okay. And then I got to handle these 2 pi radians per revolution. Need that conversion factor. That gets rid of the revolutions. Now I'm in radians per hour. But a radian is the radius 18 inches per 1 radian. They have taught you, let me just review this. Here's what a radian means. A radian is an arc length that's equal to the radius.
Okay.
If that radius, if this is 1 radian angle, and that radius is 3, then S is 3.
Okay.
If you have a 1 radian angle, the arc length is the same as the radius. And in this problem, the radius was 18 inches. So that's where I come up with this conversion. It's the length of the
Okay.
radius per 1 radian. 1 radian means the radius length. Okay?
Okay.
And that gets rid of the radians. Now I'm in inches per hour. So I got to do, somehow I got to get it in feet. So how about we do 1 foot per 12 inches.
Mm-hmm.
That gets rid of the inches. And now I'm in feet per hour. And finally, the last conversion is 1 mile per 5280 feet. The feet cancels. My units left are miles per hour. That's a linear speed. Now I still have to multiply 630 times 60 times 2 pi times 18, and I have to divide it all by 12 times 5280. But
Okay, yeah.
what I get is 67.47 miles per hour. And that's how you convert angular speed to linear speed. Okay?
Okay.
Now, your problem was slightly harder because they give you the final speed and they want to know one of these things in the middle here. What was your
Mm-hmm.
problem again?
Um, find the radius given the linear speed and the rate of rotation.
Okay, so what's the rate of rotation? What's the angular speed?
82.3 meters per second and 131 revolutions per minute.
That's linear speed. Angular speed was how many revolutions per minute?
131 revolutions per minute.
So I'm going to go up into this and do everything exactly the same, only I know the answer, and what I'm trying to solve for is the radius. Okay.
Mm-hmm.
So here's what it's going to look like. I'll try to write it small. We're going to start with our angular speed. And I still know I've got to multiply it by, let's see, they gave the linear speed in meters per second, right?
Yeah.
Okay. So I got to get rid of the minutes. So what's the first conversion I can do?
You could do 60 minutes per hour.
I want to end up in seconds, not hours.
Oh, you could do 60 or 1 minute per 60 seconds.
There you go. No, 1 minute, yeah, 1 minute per 60 seconds. In other words, the units tell you whether it's 1 over 60 or 60 over 1, because you know you got to get rid of minutes. Now I got
Yeah.
revolutions per second. Well, I know that it's 2 pi radians per revolution. That gets rid of the revolutions. And then I also know that it's the radius, which is what I'm trying to solve for, per 1 radian. That's a conversion factor that's always true. 1 radian per radius, or 1 radius per 1 radian. That gets rid of the radians.
Okay.
Now I'm going to be in the radius is going to be in meters. Remember, that's what I'm trying to solve for. So I'm in meters per second already, right? So when I multiply all of those together, I'm going to get 82 meters per second. They gave us that was the linear speed. So now is all I have to do is solve for radius. Everything else is a number.
Uh-huh.
So radius, I know my units are right. Let me just be a little clearer here. I'm not going to rewrite the units, but I'm going to write this. 131 times 1 divided by 60 times 2 pi divided by 1 times r, which is what we're trying to solve for, divided by 1, and that whole thing's equal to 82. I left the units off because I can see that the units come out to be meters over seconds, and that's what they gave us. So now it's a relatively simple equation at this point.
Okay.
Right? There's only one variable, r.
Yeah.
An equation with one variable, you can solve it.
Mm-hmm.
Do you have any questions as to how to solve that?
Don't we just multiply everything by 60 first?
And then divide everything by 131 and 2 pi. So
Okay.
r is going to be 82 times 60 divided by 131 times 2 pi.
Okay.
And that's the radius of the wheel. Now, this is kind of interesting in that the wheel ends up with pi as a part of the answer, the radius. I guess that's okay. Makes me almost feel like I made a mistake, but let me just check my math here. The first one in my problem, I had 5 conversion factors. Yeah, I had 1, 2, 3, 4, 5, 6 conversion factors. Yours only has 1, 2, 3, 4.
Mm-hmm.
That's because I'm in meters per second, not in miles per hour. So I didn't need this conversion of 1 mile per 50 to 80 feet.
Mm-hmm.
I didn't need 1 foot per 12 inches. In other words, my answer, R, has to be in meters.
Yeah.
Yeah, because I ended up with 82 meters per second. So whatever radius I end up with is in meters.
Okay.
So that's meters. Oops. And that's what radius should be in, is meters, not meters per anything. Radius is a linear measurement, so you want it to be just one thing, either meter,
Okay.
feet, or inches, whatever. Since they gave me the linear speed in meters per second, then I'm going to end up with a radius in meters.
Okay.
Okay, let me just check something here. Why does that pi not go away? It went away in the other one, did it not? Because it was, no, it didn't go away. No, I ended up with pi in my answer on the other one also. And only I had to convert it. In other words, I had to eventually convert pi to 3.14159, however many places you want, in order to come up with miles per hour.
Mm-hmm.
That my answer was in miles per hour, it was 67.47 miles per hour, even though there was a pi there.
Mm-hmm.
It was converted. So having pi in this answer is fine. You can put that into a calculator and then round it off. Not a bad way to do it, but that'll give you the radius in meters.
Okay.
Okay.
Okay. I just have one more problem.
Okay.
So it is the same thing as the last one.
Mm-hmm.
And the linear speed is 553 inches per hour.
Okay.
And the angular speed is 0.09 revolutions per minute.
All right. You try this one. Start off with the the angular. Oh, and they want you to figure out the radius again?
Yeah.
All right. Why do they always have to start you so hard? I mean, it's easy enough to figure out linear speed if you have angular speed.
Mm-hmm.
That was the first one I did for you out of my book. Figuring out
Yeah.
one of the variables in the middle is a degree of difficulty harder. But let's start off with 0.09 revolutions per minute. And knowing that over here we're in inches per hour. So that tells you some of the conversions you have to come up with.
Okay.
Okay? So what's the first conversion?
You could do, and you're going to hours?
Mm-hmm.
Oh, man.
So how do minutes and hours relate?
You could do 60 minutes in an hour.
60 minutes per hour.
60 minutes per hour.
And the reason I say per is because that tells you how to do it, and it also shows you, you're going to cancel the minutes. Now we got hours in the denominator.
Mm-hmm.
We're done with that conversion. Now all we got to do is convert revolutions to inches. And I can even put the number over here. This is 553 inches per hour. Okay. Well, let's start by converting revolutions to radians.
Okay. There are 2 pi radians per revolution.
Okay. That gets rid of the revolutions. Now we're in radians per hour. We only need one more conversion factor. 1 radian is equal to 1 radius.
1 radian is equal to 1 radius?
Uh-huh.
Oh.
So
And how many inches are in the radius? So you'd have one
radius per 1 radian.
Yeah.
Now the radians cancel, and I can see my units are, what happened to my inches? My radius is going to be in inches.
Yeah.
That's what happened to my inches. It's there, and now I end up with inches per hour, and that's what they gave us.
Okay.
So I got all the units right, so I can facilitate the solution by just ignoring the units, multiplying everything, and solving the equation.
Okay. That times 60.
Oops, times r. R being the radius. In other words, I got all 4 pieces.
So that would come out to like
60 times 2 pi. So r is going to be 553 divided by 0.09 times 60 times 2 pi. And you want to come up with a number for that.
that comes out to be 10.8.
In your lengths.
What? Sorry?
You generally, when you're asking for the length of something, like a radius of something, you don't generally want pi in your answer, especially if it's in the denominator. And it's in the denominator here. So
Okay.
in your calculator, put 553 divided by all of those and use your pi key. In other words, divide it by 0.09, divide it by 60, and then divide it by 2, and then divide it by pi. Whatever you get.
Okay, so 553 divided by 0.09 times 16 to secant pi equals,
Well, you need to put parentheses around that entire denominator if you're going to do it the way you did it.
Oh,
The
okay.
easier way to do it is to divide 553 by 0.09,
Okay.
then divide that answer by 60, and then divide that answer by 2, and then divide that answer by pi. That way you don't have to worry about the parentheses problem.
Oh, it comes out to 16.29.
And that's a very believable answer for the radius of a wheel.
Okay.
Okay?
Cool.
In other words, they don't make wheels that are half an inch in radius, and they don't generally make them that are a mile in radius.
Yeah.
Talking wheels, you're talking this neighborhood here.
Uh-huh. Okay. Cool. That was my last problem for today.
Well, good, because we're out of time. So. All right, Nick.
Yeah.
Like I said, they start you out with the hardest stuff. I consider tonight's material really harder than the unit circle stuff we did.
Mm-hmm.
And I really think they should be taught in opposite. They should teach the unit circle stuff first and then this stuff. Just because you don't learn to ski by starting on the hard slopes, you learn on the beginning slopes, and then you go to medium, and then you go to hard. And that's the way math should be taught, in my opinion. And that's why I'm so key to start everybody out on trig on the unit circle, because ultimately it's that unit circle stuff that you have to know. Not this so much. When you get to the end of your trig course, you're probably not going to see a problem like this.
Yeah.
Put this in the beginning chapter, and then they go on from there. I would almost bet you money that once you're done with these problems, you will not see one again like these. Where you're, by one like these, I mean where you're dealing with angular speed and linear speed.
Yeah.
You will not get another one of those problems.
Okay. Okay.
But we know how to do them. The key is the unit.
Yeah.
And the key with the units is knowing that you have 2 pi radians per revolution and that you have a radius per radian. This is the hardest one to remember. This radius where you have one radius per 1 radian. That conversion is necessary when you're doing any of these angular and linear speed problems.
Yeah. Okay.
So one thing you figure out from this is that if you can double the size of your wheel, you can increase your linear speed by a lot.
Oh, yeah.
If you went out to your car right now and you were able to put bigger wheels on your car, as long as you can get them to revolve at the same rate, number of revolutions per minute, your car is going to go faster.
Huh.
Yep. No lie.
Huh. All right. Cool. Huh.
That's why they used to have bicycles that had giant front wheels. You can make that front wheel rotate pretty fast. And a wheel that's twice as big is going to make you go twice as fast.
Okay.
Right?
Cool. Thank you, Mr. Cohen.
You're welcome, Nick. I will talk to you next time.
Yep. Talk to you next time.